Hey guys, welcome back. This is going to be the second part of the 8.1 instructional video. And really, my whole goal in this video is to dig a little bit deeper on the introduction you were provided on in the part 1 of 8.1 instruction. If you haven't watched that yet, please go back, watch the initial 8.1 part 1 instructional video from Khan Academy. It's going to give you an introduction to negative exponents and some of the basics behind it. And so in this video, kind of building on that, what I want to do is provide maybe an alternate explanation. Maybe you watched the initial video and you were like, I get the process of finding negative exponents, but I'm still really not sure why. Why are negative exponents fractions? Why are they not negative numbers? And so I wanted to provide you a bit of intuition here and dig into a little bit of where we get the idea of negative exponents, and how we get that process for solving them. So to do that, I want us to look at a table, and I'd encourage you to copy it down in your notes. What we have here is we have 3 columns. The left column representing 2 to the x in general, x being various numbers, various exponents, various integers that we will see. So we have 2 to the x, 5 to the x, and 10 to the x in the rightmost column. And what we're going to do here is I want to simply fill out this chart together. Shouldn't be too incredibly difficult. And then we're going to talk about what patterns we notice. This is going to be the primary focus. I know you all can solve exponents, simple numeric exponent problems like this, but I want to dig into the patterns. Well, first things first, let's remind yourself what an exponent is. An exponent, like 2 to the second or 2 to the third, tells us, hey, this is how many 2's you are going to see multiplied together. So when I see 2 to the third, this says, hey, there are going to be 3 2's multiplied together. Okay, if you want 5 to the fourth, hey, there are going to be 4 5's that are multiplied together. Okay, so we hopefully understand that idea of an exponent. So let's fill in, without further ado, fill in the table. 2 squared, which is 2 times 2 would be 4. 2 to the third, which is 2 times 2 times 2 will be 8. And 2 to the fourth will be 16. 5 squared, 25. 5 to the third, which is 5 times 5 times 5 is 125. And 5 to the fourth is 625. 10 squared will be 100. 10 to the third will be 1,000. And 10 to the fourth will be 10,000. And so now that we have this filled in, again, I'm sure you are capable of doing that. Let's think about what patterns we noticed. And off the cuff, right, without thinking too deeply, I noticed that as each column goes down, the numbers decrease. And as each column will go up, consequently, they would increase. But I think we can get a little bit more specific than that. Well, let's see what patterns we can find here. 16 to 8, maybe my initial gut reaction is, oh, maybe we're subtracting by 8. But we quickly learned that that will not be the case going down all of the columns, and that only applies going from the 16 to the 8. But then maybe we look at this and say, hey, you know what? To get from 16 to 8, we can divide by 2. And hey, that pattern continues for the column or the row below. Okay, and progressing down our rows, we divide by 2. Well, let's see if that pattern's consistent. And we quickly see that from 625 to 125, we aren't dividing by 2, but we are dividing by 5. And so maybe the broader pattern that we're observing is not dividing by a specific number, but we're dividing by the base as we move down column. And we find that that pattern is consistent here as well. We divide by the base as we move down the column. Write that a little bit cleaner. Okay? And really, let's take a moment and appreciate what's happening here. As we go down the column, what's occurring? The exponent is decreasing by 1, and we are dividing by the base. Okay? Or another way of thinking about it, instead of dividing by 2, maybe we could also think about it as multiplying by 1/2. Okay? Again, those are the same thing, right? Division by 2 is the same thing as multiplying by 1/2. So broadly speaking, what we're observing here is as the exponent decreases by 1, our value of that 2 to the fourth or versus 2 to the third will decrease by division by the base. Okay? When my exponent 2 to the fourth goes to 2 to the third, I will divide by the base, okay, or multiply by 1 over the base. And hopefully this makes sense, right? Because if we think about it the other way, right, when we increase the exponent, if we were to move up the table, we would, instead of, if we go from 2 to the second to 2 to the third, what we would multiply by the base, or multiply by 2. And this should make sense, given that 2 squared is 2 times 2. 2/3 we know is 2 times 2 times 2. So if we're going up the table, if we want to go from 2 squared to 2 to the third, we are multiplying by an additional 2. Consequently, if we're going from 2 to the third to 2 to the second, we are multiplying by 1 less 2. And so we would need to multiply by 1/2 or divide by 2. So broadly speaking, the pattern we're observing here is as the exponent decreases by 1, we divide by the base, or an alternate way of thinking about it, we multiply by 1 over the base. Okay? So this is the pattern we're observing. Let's see if it stays consistent as we keep going. So again, another table, same columns, different exponent values though. And I think maybe it'll be helpful for us, if I write the last value from the table above. You, of course, already have this on your paper, so it's probably a little easier for you to see than me. And so let's stick with the pattern and let's complete this table, okay? We have observed the pattern that is if the exponent decreases by 1, I can find the overall value by simply dividing the previous value by the base or multiplying the previous value by 1 over the base, okay? So from 2 squared equals 4, if I keep with that pattern, because while in the other chart it was very obvious what the values would be, we know what 10 squared, 5 cubed, we can find those easily. I notice some negative exponents down here, and I don't really know how to calculate those off the top of my head. But if I follow the pattern, I can easily figure out what they are. So sticking with the theme that if we increase the exponent or decrease the exponent by 1, right, 2 becomes 1, all I need to do is divide by the base or multiply by 1/2. So I multiply by 1 over my base. 4 times 1/2 will give me 2. If I continue this pattern of multiplying by 1 over the base, because I notice the exponent keeps going down by 1, 2 times 1/2 is 1. 1 times 1/2 is 1/2. 1/2 times 1/2 is 1/4. And so what we see here is if we continue following our pattern that each time the exponent decreases with the same base, I can find the next value by multiplying my previous value by 1 over the base or dividing by the base. And when I do that, maybe I'll erase these so just it's a little bit easier to see, we can find our values, not just for 2 to the first and 2 to the 0, which you probably already knew, but we see by our pattern what the negative exponents turn out to be. 1/2 and 1/4. And we'll dig into that in a bit. But let's continue this maybe for the other ones, right? Again, my exponent is decreasing by 1. My base is consistent. So I take my previous value and I multiply it by 1 over the base. Or again, don't forget this is the equivalent of dividing by the base. And what I end up with here is 5. If I do this again, I end up with 1. And then I end up with 1 over 5. And then I end up with 1 over 25. Doing this for 10. I get 10, 1, 1 over 10, and 1 over 100. And so what we've observed to this point is when we were in our previous table, we observed a pattern. We know the value of these exponents, and by looking at what these exponents are, things like 10 to the squared, 10 cubed, 5 to the fourth, by looking at the relationships in the columns, we noticed that as the exponent decreased by 1, all we had to do to find our next value was divide by the base. Okay? To get from 2 to the fourth to 2 to the third, I just need to divide 16 by the base of 2. Or, thinking about it a little bit differently, multiply by 1 over the base. Okay? Because that and dividing by the base are the same thing. What this allowed us to do, if we continued this pattern, was to discover the value of some negative exponents. Okay? So by intuition, by following logic and mathematical patterns, we discovered the value of some exponents. Now let's explore that relationship maybe a little bit more. Again, I'm going to erase these. Now, if at this point you're like, Mr. Carter, I don't understand where these values are coming from, I'm not quite picking up the pattern, pause the video and shoot me an email and we can dig a little bit deeper into that. But for now, we will move on understanding that by the logic, as the exponent decreases by 1, to find the next value, if our exponent decreases by 1, we simply can divide by the base or multiply by 1 over the base. And so we end up with these values here. Actually, I want to leave these values. You'll see why in a second. These are again from the previous table. Give myself a little bit more space. And so from using the logic of the pattern, moving down the table, we can see some more patterns start to develop. And what are some patterns that hopefully we notice? Well, before I get into them, pause the video and see what patterns you observe. So the patterns I see present here, and this is probably not a new rule to you, you probably already know this, but again, by intuition, we have quote unquote discovered it. Anything to the 0 power ends up with a value of 1. Any number to the 0 power ends up with a value of 1. And we can see that in our table here. Whether we were working in the 2 column, the 5 column, and the 10 column, when it got to that number to the 0 power, it turned out to be 1. Okay? And this will apply for any number except for 0, which I won't dig into in this video, but if you would like to learn more about that, you let me know. Another pattern I observe is anything to the first power is itself, or just the base. 2 to the first is 2, 5 to the first is 5, 10 to the first is 10. Anything to the first power is itself. Again, we've discovered this by intuition, simply using math logic and the patterns we observed. Now, the other thing I notice is, and those first two rules probably aren't that new to you, but the other thing I'm noticing is one, that all my negative exponents here have become fractions, and I think we can observe, actually let me erase the other boxes so we can really focus on this. I think what we can observe is even a deeper pattern here. Not only are all these fractions, but there's a relationship between these and their positive counterparts. What do I mean by that? Well, let's look at the 2 column. What we notice here is that, and maybe I'll expand on it a bit down here, we notice that, let's use a different color. We notice that 2 to the first, as we saw, is 2. Okay, we observe that via intuition, just following our pattern. What's interesting is that 2 to the negative 1 is 1 over 2. 2 squared is 4. 2 to the negative 2 is 1 over 4. If we want to continue this pattern, we even take 5 to the 2, we want to observe it one more time, And we notice that 5 to the negative 2 is 1 over 25. And so we see a really interesting relationship here, where in general what we're seeing is we're seeing A, or if in general, if we were to maybe summarize this, maybe we do it in a different color so that we really can see it. What we're observing in general is if I have A to the x, then or A to the x equals y, then A to the negative x equals 1 over y. Okay? When I have a base to a power, the base to that negative power is 1 over the solution from the other one. Okay? And we can expand this idea even a little bit further. And this is really where your rule of negative exponents comes from. If I dig in a little bit more to this relationship here, 2 squared equals 4, and we have 2 to the negative 2 equals 1 over 4. We can get our full rule of exponents by looking at this idea right here. If 2 squared equals 4, then we know by substitution that 1 over 4 could be rewritten as 1 over 2 squared. By the idea of substitution, right? We know 4 is 2 squared. And so 1 over 4 could be rewritten as 1 over 2 squared. Maybe it'd be helpful to see this again, right? If we look at 5 squared is 25, and 5 to the negative second is 1 over 25, then how could I rewrite 5 to the negative second? Well, if 5 to the second is 25, then 1 over 25 can be rewritten as 1 over 5 to the second. And this is where your rule, or maybe I'll condense these together. This is where your rule for negative exponents comes from. And this is kind of intuitively where this came from, right? We see by our pattern, right, that by decreasing the exponent by 1, our value, we can find our next value down the table by simply multiplying by 1 over the base, or dividing by the base, right? To get from 2 squared, if 2 squared equals 4 and I decrease that exponent by 1, I can find the next value of 2 by simply taking the previous value of 4 and dividing it by 2, or multiplying by 1 over 2. By following this pattern, what we observed is we quickly found out some values for negative exponents. And when we dug a little deeper and looked at those values for negative exponents, what we saw was a relationship between the positive exponent and the negative exponent. Namely, that the positive exponent and the negative exponent were the same, except the negative exponent had the value of the positive exponent in the denominator, which leads us to this conclusion. When the exponent is negative, the value will become a fraction with 1 on top and the base to the exponent on the bottom, except if the base is 0. A little bit confusing of a definition, but basically what we're saying here is if I have 3 to the negative third, or maybe let's start with an example that we've seen before. If I have 2 to the negative second, that value, which we know, by the way, which we know is 1/4 from previous examples above, that value, 2 to the negative second, will be a fraction with 1 on top and the base to the exponent that's positive on the bottom. So when the exponent is negative, your value will be a fraction, the value of that base to the exponent will be a fraction with 1 on top and that base to the positive exponent on the bottom, unless the base is 0, which would lead to a division by 0, and we're not going to work with that. Okay? So broadly, the shortcut, and I think this is what the Khan Academy video concluded with, if we have something like 3 to the negative third, we can quickly find the solution to that by simply writing 1 over 3 to the third, which makes our exponent positive. And then, of course, we can solve from there by understanding what 3 to the third is, and we get 1 over 27. And this is some intuition on where your rule for negative exponents comes from. Okay? So again, another way, I know the Khan Academy video presented one way. This is a little bit different way of kind of discovering and seeing, why do we have this rule for negative exponents? Why is it that I can take a negative exponent and put it in the denominator of a fraction with 1 on top, and that works, and that's how we find our negative exponents? Hopefully the table and the chart and the explanation gave you some intuition. I know it can be kind of thick and deep to think about, but again, hopefully that kind of gives you some understanding as to why we have the rule of negative exponents.